This conference will now be recorded.
Hello everyone. Last day we have started this chapter, that is coordination compounds, and we have already started the part classification of ligands. That is, there are different types of ligands maybe there, and how many different types are there, that we will see. Polydentate ligand. So monodentate, bidentate, these two we have already seen. Polydentate ligands. So the ligands which coordinate with the central ion through more than two donor atoms. So if it is one atom, it is monodentate. If it is two atom, it is bidentate. But when it is crossing the limit of two, that is more than two donor atoms, in that case, that will be present in the ligand. Then they will be called polydentate. Now it may be tridentate, tetradentate, etc. So here we will see the examples. Tridentate ligands. So from the name, it is clear that here denticity is 3. So in these examples, two examples we have under this category, that is tridentate ligands. Diethylene triamine. Now ethylene diamine, what is the structure? That is that we have seen under the category of bidentate, which is NH2, CH2, CH2, then NH2. So this molecule is known as ethylene diamine, in short EN. So ethylene, it is because of these two carbon, and diamine because two NH2 groups are present. Now when it is the tridentate example, now this ethylene part, that is coming see twice, CH2, 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 CH2. So that is why we are saying now it is diethylene, and this two CH2, CH2 fragment is joined by NH, and in the terminal position there are two NH2. So total number of nitrogen is 3. So that is why donating site 3. And the name, try to understand the name. En is ethylene diamine, but this structure is diethylene triamine because total 3 NH group is there. This NH group is in between, so that is why it is secondary amine, and the terminal 2 NH2, that two are primary amine. So this molecule, in short, diene. Another example is 3 pyridine ring, they are attached to each other in the ortho position. See, these are the ortho positions, and 3 donating sites are there. So the name is 2, 2 prime, 2 double prime, terpyridine. In short, terp, TERPY. Next example, tetradentate. Here we have porphyrin ring. So this type of ligand, it is naturally available actually. So in bioinorganic chemistry, you can see this type of example. So porphyrin ring, this is a cyclic structure, and 4 nitrogen donating sites are present. See, so the metal atom that will be present inside, it will be coordinated by 4 nitrogen atoms from 4 sides. Fine. Another example is TREA. This is the short form, train. And what is the full form? Full form is trees. Trees, when we use, it is just analog of tri. That is, if any moiety is coming 3 times, it will be trees. Trees in bracket, first bracket, 2 amino ethyl. Amino ethyl is this group. Ethyl is 2 carbon chain, and amine group is there. So 2 amino ethyl, and it is 3 times attached to this nitrogen. So as if it is the structure of that is this nitrogen with which 3 groups are attached. This is actually 3-degree amine. So R3 amine, where R group is as if the CH2, CH2, NH2. Okay, so this molecule is train, and then another example is triene. Now this is actually the extended version of diene. So when it is diene, you have total 3 NH amine part and 2 ethylene part, but now it is triethylene. Triethylene means see, CH2, CH2, it is coming thrice. And when it is coming thrice, in the joining point there will be 2 NH, terminal position there will be 2 NH2. So now the name is triethylene tetraamine. So once you can understand the name of EN, that is ethylene diamine, which is example of bidentate ligand, you can easily identify the name for the 2 extended version. That is, the next extended version will be diene, and the next one is trilene. Okay, so up to this in the structure of ligands and then in their denticity, is there any doubt? After tetradentate, hexadentate example, a very good example under this category is, in short, EDTA. And what is the full form? It is ethylene diamine tetraacetic acid. And it remains in with 4 negative charge. So that is why it is, we can call it tetraanion of this acid. Because when we are saying that it is tetraacetic acid, that means 4 CO2H group must be present. But if all the CO2 are present in the form of carboxylate, CO2 minus, then what you call? You will call it anion of the acetic acid, or you can say it is acetate. Okay. So tetraanion of ethylene diamine tetraacetic acid. And see, it is actually ethylene diamine derivative. Ethylene diamine is this molecule, NH2, CH2, CH2, NH2. Now, if you replace these two hydrogen, both sides, by the group CH2, CO, minus. So you are replacing all the 4 hydrogen with CH2, CO2 minus, and then you are getting this type of structure. So that is why the name is ethylene diamine tetraacetic acid, because acetic, it is also acetic acid derivative, right? Acetic acid is CH3COOH. But suppose if you are removing one of the hydrogen from the CH3 part of acetic acid and you are joining it to this amine. So that is why the name tetraacetic acid. And why it is having 6 donating site? So there are actually total 4 O minus site, 4 O minus, that is anionic, and 2 neutral nitrogen. So 4 O minus and 2 neutral nitrogen, together it is 6. Okay. Now here how it is coordinating with metal. See, this is the central metal, and 6 coordination side means it is octahedral geometry. So these two positions, cis positions taken by nitrogen, then O minus, another 2 O minus. Okay. So see here the formula will be like this, MEDTA. That means just a single ligand is fulfilling all the 6 coordination site because its denticity is 6. So per metal atom or ion, there is just presence of one ligand, one EDTA. Okay, because per ligand you are getting all the 6 coordination site. And remember, 4 anionic site, 2 neutral. Because this information is important and question based on this is very common. So in this slide, is there any doubt? So under polydentate ligands, we have seen tridentate, tetradentate, and hexadentate example. Okay. Now we will see some other type of ligands. Other type of ligands, the first that we are going to discuss is chelating ligand and chelates. So the ligands are called chelating ligands, and after binding to metal, the ring structure that will be formed, that is actually known as chelate. When a bidentate ligand or a polydentate ligand, that means if you want to get chelate, you have to use minimum bidentate. You cannot use monodentate, because if it is monodentate, ring formation is not possible. So minimum bidentate required, and if it is tridentate or tetradentate, it is fine. So when a bidentate or polydentate ligand is attached through 2 or more donor atoms, 2 is for bidentate and more is for polydentate, to the same central metal ion, and obviously it will form a ring structure, because if anything is bidentate like this and if it is attached to metal, a ring will be formed. So this is a ring, and this ring is known as chelate, because this ring is formed by chelation. That is why the name of the ring is chelate. And this type of specific kind of ligand, that is, they are known as chelating ligand. So in this molecule, copper is attached to it, 2 ethylene diamine. See, and charge outside the coordination sphere 2 plus. So this is one En, this is another En, and how many chelates we are getting? 2. This is one 5-membered ring, this is another 5-membered ring. Fine. Then here we have the next picture. nickel, and the ligand is CH3 C double bond N OH, and this side also there is CH3 C double bond N O minus. Okay. Now, as it is a coordinate bond from nitrogen to oxygen, so that is why this type of arrow is there. Okay, it is actually glyoxine. This type of ligand is known as glyoxine, and nickel dimethyl glyoxine, that is the full name of the ligand. In short, it is known as DMG. Now, glyoxine, how we are getting this structure? CHO. This molecule is known as glyoxal. Okay. Now, if you are forming two imine in both the carbonyl, what type of structure you will get? You will get double bond N OH. That means you are treating this molecule with hydroxylamine. So now it is this two hydrogen and this oxygen together, it will form water and it will be removed. And finally, you are getting this type of structure. Okay. So this is glyoxal and this is glyoxine. Okay. And after that, if this hydrogen is replaced by two methyl group, basically you are getting this structure. So that is why the name is dimethyl glyoxine, DMG. Okay, nickel DMG2. And part DMG, there are two donating site, because one hydrogen, if we remove, there will be O negative charge. Fine. So one OH, another oxygen is O minus, and the other side it will be opposite. Now OH and O minus. Okay. But donating site is not oxygen, here donating site is nitrogen. And what happens? There is hydrogen bond formation possible between this oxygen and hydrogen. So why I am going into detail of this DMG structure? Because question based on this is also frequent. Fine. So be very careful about the structure of dimethyl glyoxine, because this structure is this, that is the example of nickel dimethyl glyoxine complex structure. The example of it is very good. Fine. Any doubt in that structure? So this is 2-dimethyl glyoxine, and in each side you are getting a 5-membered ring. See, this is a 5-membered ring, right? So oxygen is not donating site, and this O minus, it can form this type of hydrogen bond, both sides. So that is why the complex is so stable. Okay. Next example, flexidentate ligand. Some ligands exhibit variable denticity, and that is why they are called flexidentate. Now, variable denticity, the meaning of this term is sometimes it can behave as, suppose, monodentate, sometimes it can behave as bidentate, or sometimes it is behaving as bidentate, sometimes tridentate. That means what? There is availability of more than one donating site, but it is not using all the donating site simultaneously. That is, sometimes it is using simultaneously, sometimes it may not use. So take this example. This example is basically sulfate ion, SO4 2 minus. So now these two O minus, these two are the donating site, but both the donating site may not be used simultaneously. So suppose if it is used together, then it will be forming this type of ring structure, because it is now behaving as bidentate. But another way also it can behave is that now it is behaving as monodentate. That means this O minus is not donating, acting as donating site. So now it is monodentate, but in the previous picture it is bidentate. So this is another kind of denticity, variable denticity, that is possible. And because of this type of nature, flexible nature, it is called flexidentate. Next term is ambidentate. Ambidentate ligand, it will always have more than one type of donating site, and each time it will use only one donating site. both the side will not be used simultaneously. So only one side is utilized at a time. And example is, here we have taken NO2. So NO2, it can bind through metal, through nitrogen or through oxygen. So when it is using nitrogen atom as the donation site, then it will be called nitrito N. But when it is using oxygen as the donating site towards metal, it will be called now nitrito O. Another example is SCM, thiocyanate. So both side, or one side we have sulfur, another side we have nitrogen. So now the name we are using thiocyanate. SCN is cyanato, but when a sulfur is there, it is thiocyanate. And if it is donating through nitrogen, that is the second picture, now it will be called isothiazide. Okay, so two different types of donating site here present, N or O. In the second case, S or N, but together, that is simultaneously, it is not using both of them. Only one is using at a time, but two possibilities are there. Okay, any doubt in this slide? Next classification of ligands, that will be on the basis of bonding interaction between the central metal atom and ligand. So until now, we have when we have discussed classification of ligands, we have not used metal. So there is specifically any metal orbital or interaction is not talked about. Fine, but now in this case, when we are classifying it based on how it is interacting with the central metal atom, so this is a completely new basis, that is based on this we are doing this classification. So this is completely something new, because here the interaction between metal atom and ligand will be considered. The first category is classical or simple donor ligand. So here all these examples that you are seeing, that is very common and very simple to understand. So they use their lone pair of electrons to the central atom, or it may use the negative charge. Fine, both are possible. But remember, all these are simply donating. That is, there is no other thing going on between the metal and the ligand donating site. But there is a type which is known as non-classical. Now see, this is classical, this is non-classical, and they are not very simple. They are known as pi acceptor ligand. So in this type of ligands, you will see there is a presence of pi bond also. And because of the presence of this pi bond, something is happening which you have not seen in case of simple donor ligand like all this. So what is happening here? First, these ligands donating the lone pair of electrons to the central atom. So up to this, it is normal that we know that ligands are donating electron density towards metal. Nothing new in that. But what happens? This is not the end of story here. What happens now? Metal can also donate back. That is, now the direction of electron donation is from metal towards ligand. So the ligands now they are accepting the electron cloud from the central metal atom, and where it is accepting in the low lying vacant orbital. So there are some vacant orbital, mostly it is anti-bonding pi star orbital. And why it is low lying? Low lying means which is lower in energy. So as it is lower in energy, it can easily interact with the, I mean to say, they can easily accept electron from the metal. So this kind of back donation. Why it is back donation? Because first ligand is donating, then metal is donating. So that is why it is known as back donation. And the effect is known as synergistic effect. So see here the examples of ligands that you are seeing. In all these cases, most of the cases there is presence of pi bond is there. Okay. And we will see the picture here. So see, this is the metal center, and in metal first this d orbital it is filled. Oh, sorry, this metal d orbital is vacant. So in this vacant d orbital, CO as ligand, it is donating electron density through carbon. Remember, it is also very important. In metal carbonyl complexes, if it is asked that is it donating through carbon or is it donating through oxygen? So the answer will be it is donating through carbon, not oxygen. So that is why we have written carbon here. It is donating electron towards metal. It is normal, that we have already seen. But after that, what is happening? Now the field orbital of metal. Now this is field d orbital of metal. Now it is donating electron to the pi star of CO. So this bond is actually pi star. So phase are not matching. So that is why the orientation of the orbitals are like this. So now metal is donating its electron density towards ligand. And this is known as back donation or synergistic effect. Back bonding also you can. Now because of this both side, I mean to say both direction, as there is donation going on, ligand to metal, metal to ligand. So that is the reason these type of ligands are actually very stable complex. Okay, because here a two-way electron donation is occurring. So that is why they are very stable. One more example with phosphine ligand. This example is with metal carbonyl complexes. Metal carbonyl complexes are, that is the reason, very stable. So what happens in case of phosphorus? Here we do not have any pi bond, though in most cases you will find pi bond. But still see what is happening. First, metals dx square y square orbital, it is vacant, unoccupied. So phosphorus is donating electron pair towards metal. This is metal d orbital dx square y, and this is sigma bond. Okay, so it is the field p orbital of phosphorus, through which it is bonding towards metal and it is donating electron density towards metal. Next, what is happening now? Pi accepting or back bonding. Now phosphine, it also has sigma anti-bonding, because here pi bond is not present, so we cannot talk about pi star. But here sigma star is present. So this sigma star is basically unoccupied or vacant. So that is why now metal, it can donate electron density. Metal's dxy orbital, suppose it is occupied and it is donating electron towards sigma star of phosphine. Okay, so see here phosphine example is there, PR3, where R may be H, that means PH3, PET3, PPH3. PPH3 ligand is very common. It may be PF3 also. Okay, so this type of pi back bonding, that is possible in all these examples that are given in this category. Okay, so is it clear? What is the difference between classical and non-classical ligands? So sometimes some ligands can be given in any question and it can be asked that in which ligand pi accepting is possible. Okay. Any doubt? And another thing that I want to mention here, suppose CO is common. In one case there is a metal M, another one is M prime, that is different metal. Now when metal is donating electron towards CO, what will happen? The bond order between CO, that will decrease, because when metal is donating electron towards carbon, the electron density now it will be over oxygen. So this triple bond nature, that will be diminished and double bond nature will be increased. That means bond length of CO will increase when back bonding is very high. But if back bonding is very low, then CO, it will have this triple bond type of nature. But if back bonding is very high, now there will be double bond kind of nature. That means bond length will decrease, because triple bond is always shorter in length compared to double bond, and double bond is shorter in length compared to single. That we know. So in this way, suppose in case of M and M prime, if we compare, M is better to donate electron density. It may be that metal is having lower oxidation state +1, but another case that is having higher oxidation state +3. Now as it is more electron rich, because its oxidation state is less. So electron rich metal means what? Back bonding will be very high And when back bonding is very high, the CO bond order will decrease. That means from bond order 3, now it will decrease to 2. That means bond length will increase. So in this way also, that is a question based on this is also very common. And remember, when bond length is decreased, the stretching frequency of CO, which is denoted by this new CO, that will also decrease or increase. So all this based on this pi back bonding, different types of questions may be formed. Okay. First of all, is some ligands will be there, and it can be asked which one will be able to form, behave as pi acceptor. Then another example may be in which case CO bond length will be high, in which case CO bond order will be high or low, and then stretching frequency related question also may be there. Okay. Next is nomenclature. Now we say that it is IUPAC rules for nomenclature because the full form of it is International Union of Pure and Applied Chemistry. So IUPAC nomenclature, it is not something new you are seeing here, because we also use it for inorganic chemistry. Fine. So the formulas and names which will be used for this coordination type of compounds, these are actually based on the rules of IUPAC. Fine. Now one by one we will see the rules. Rule number 1. When we will name a coordination compound, we know there is a cationic part, there is anionic part. So if you take particularly this example, sodium is present outside the coordination sphere. It is carrying +1 charge, and obviously the charge outside the coordination sphere, it will be -1. And the moiety that is present inside, CONH3 whole 4 Cl2, it is together forming the anion. So here the fact is, the cationic part will always be named first, after that anion. And it is very easy to remember. Why? Just take the example of sodium chloride. How we are using, how we say the name? We say sodium chloride. Okay, chloride, not chloro. We never say it is chlorosodium. So sodium we are saying first, then chloride. That means you are using the name of the cationic part first, then the anionic part. Okay. So same thing you have to follow here. So cation is always named before the anion, irrespective of the fact whether the complex ion is cation or anion. Now what is the meaning of this last line? In this particular example, this part is anionic. That means the coordination part is anionic. But another example may be also possible. Suppose here you have any moiety inside, that is not important, but outside, suppose +1 charge, and outside there is Br-. Now the coordination part is forming the cation, and the outside there is counter ion, which is anion. So that is another possibility. So whatever is the case, whether it is this type or this the second type, always you have to name the cationic part first. So for the second example, you have to name this part first. After that, it will be bromide. Okay. So here, how will be the name? We are writing sodium first, and then rest of the part, how it is done, that we are going to discuss one by one. Right now, just remember, cationic part named first. After that, the anionic part, which is in this case the coordination part, but reverse may be also the possibility. That is the second one. Okay. Rule number 1 clear? Second rule, there may be more than one type of ligands, and that is the most common thing you will see. So just take the previous example. Here cobalt is having two different types of ligand, ammonia as well as Cl is there. So when there is more than one type of ligands present in any coordination compound, the name of the ligands is to be done in alphabetical order. So take this previous example. Here we have ammonia, which is starting with the alphabet A, and chloride, it is starting with the alphabet C, and A comes before C alphabetically. So that is why we have used tetraamine first, then dichloro. So alphabetical order you have to follow, followed by the name of central metal. So first you write the name of the ligands as we have done here. So first here the name of the ligands are mentioned, two types of ligand, and then the metal name is used. Okay. Now if the ligands are anionic in nature, for example if it is chloride, fluoride, bromide, cyano like this, it will always end with O. Okay. And it is not the end here. See, anionic ligands end in O. For anions that end in ide, for example, chloride, Cl minus, how we are writing it? Chloride or bromide. Okay. So it will be ide for in some cases, it will be O in some cases, and it will be 8 in some cases. That is sulfate, nitrate. So it is not that it is always ending with O. Different examples are there. So when it is anionic ligands that are ending with O, okay, then another possibility is ide, another possibility is 8. So see what is happening when it is IDE, that means chloride, bromide. Now it will change to O. Okay. And the ligands that are present as 8, for example, cyanate, sulfate, that will be changed to sulfato, nitrato, like this. Okay. And if any ligand is there which is ending with ite, for example nitrite, then it will be changed to ito, that means nitrito. So remember, once again I am repeating, if it is ide, that is normally if we use the term ide, it will be O, that is chlorido, bromido, like this, or chloro or bromo. And if there is any 8, that will be changed to ato, that is sulfate to sulfato, nitrate to nitrato. And if there is ITE, for example nitrite, it will be changed to ito, that means nitrite to nitrito. So in this way there will be some change. But remember, this is only for anionic ligands. It is written in bold, only for anionic ligands. Okay. Any doubt up to this? So if this is for anionic ligands, what about with neutral ligands? For example, water, ammonia, like this. So for neutral ligands, it is a simple common name of the molecule will be used. Exceptions are also there. So there are some important exceptions. These three ligands, water, ammonia, carbonate. So here we are not using the common name. What we are using instead? We are using aqua, amine. See, it is double M. If you are writing single M, it will be wrong. Double M is the correct spelling. And CO, carbon. We are not writing carbon monoxide. That is not correct. Normally what we say, common name is carbon monoxide, then water. But here what you are using, aqua, amine, not ammonia, carbonyl, not carbon monoxide. So these three are actually exception. But except these, if there you are finding any other neutral ligands, then common name will be used. Though it is also true that mostly the neutral ligands that you will get, it is either ammonia or water, most of the time. Okay. So in rule 2, which is comparatively complex, so if any doubt, please tell me. I will repeat it once more. Is it clear? Here we have some examples for anionic ligands as well as neutral ligands. So Br minus, F minus, HO minus, Cl minus, then oxalate and carbonate. Okay. So oxalate and carbonate, these two are basically ending with 8 under normal condition. So now it is changed to A2. Okay. And these are hydroxide, cyanide, bromide, fluoride, that means IDE. And now it is changing to O. So see, IDE changing to O, ATE changing to A2. Fine. and the second part neutral ligand. So these three are exception. But suppose if you have neutral ligand nitrogen or oxygen, see, we have used directly the common name. And ethylene diamine, this is the normal common name that we use if the ligand is simply present, and when it is present with metal and interacting with metal, then also the name is same. It is still ethylene diamine, no change. But only these three, there is some exception. Any doubt? Rule number 3, if the name of the ligands already contains numerical prefix. Okay, what it means? So suppose just take the example of ethylene diamine. Here you already have used the term di. So there is already some numerical prefix. So if ethylene diamine is coming thrice or twice, then you cannot use this di once more, because already in the name there is di. But still, if there are two ethylene diamine attached with metal or three ethylene diamine, then what you will write? You will not write triethylene diamine. That you cannot do. So what you will do? You have to use bis for if it is 2, tris if it is 3, tetrakis if it is 4. Okay, so terms are different. And the ligand to which they refer being placed in parentheses. That means after writing bis, next, you have to place the name of the ligand within first bracket. So if you take this particular example, nickel is coordinating with 2 chloride. This is monodentate, fine, and it is also coordinating with PPH3. Now, PPH3, the donating site is phosphorus. That is nickel, it will be attached to through phosphorus like this. So this is also monodentate. But remember, in single molecule, the name is triphenylphosphine. The name of PPH3 is already triphenylphosphine. So you have already used the word tri. But now you have two PPH3. So what you will do? After writing dichloro, now you have to write bis, not di. If you are writing di, it is wrong. Bis triphenylphosphine within bracket. So as if PPH3 is coming twice. So that is why this, and then the name of the ligand. And here we have mentioned chloro first because C alphabetically comes before P. Okay. Number 4. After naming the ligand, so until now all the rules that we have discussed, that is based on, we have focused on the ligand nature. Okay. Now after you are done with this, after naming the ligand in alphabetical order, next you have to consider central metal atom or ion, depending on the metal atom is neutral or carrying some charge. If the complex ion is cation, metal is named same as the element. If the complex name is anion, the name of the metal ends with suffix "ate". What is the meaning of it? See, suppose the coordination sphere, it is carrying some positive charge and then there is Br minus. And inside, suppose there is any metal M. So in this case, the complex ion is cation, this is cation, where actually the coordination complex is present. And metal is part of that coordination entity. So that is why here when you will write the name of the metal, you will simply write the metal's name. So if it is cobalt, you will write cobalt. If it is copper, you will write copper. But if it is part of anion, suppose now you have another type of complex K2, and then inside the coordination sphere you have some metal. So now 2 positive charge and this is carrying 2 negative charge. So now the coordination part is basically anion, and metal that is belonging to this anionic part. Now when you will write the name of the metal, you have to use the suffix "ate". So if it is cobalt, you have to write cobaltate. If it is iron, you have to write ferrate, like this. And mostly It is based on the Latin name. Okay. Now see here we have some example. Metal name copper, and actually when you will write the suffix ate, what you will write? You will write cuprate. And if you are thinking where from this term is coming, it is basically coming from Latin name. You don't have to remember the Latin name. It is just given so that you can understand where from these anions are getting this type of name. So gold in Latin, it is called aurum. So the anion, that is, if gold is part of the anionic coordination sphere, you have to use the term aurate. It is ending with ate. So it is not that just after gold you are writing ate, gold ate. No, that is not correct. It is not ironate, it is not leaded. You have to write ferrate for lead, plumbate for silver, argentate, and all these new terms that you are getting. See, plumbate, it has no similarity with lead, but still we are using it because it is coming from Latin. Then argentate for silver, because silver in Latin it is called argentum. Fine. So is this clear? Rule number 4. When you will see the examples, it will be more clear. If any doubt is still there, should I repeat? Number 5, the oxidation state of the metal in the complex. You have to write it always in Roman numeral. So see the examples. Just take this example. Here, the oxidation state of nickel we have mentioned with Roman numeral. But suppose if you are writing nickel and in bracket you are writing 2, that is not the correct way. Don't do this, okay? So sometimes in options different name will be there, and if it is asked, choose the correct one. If in any option there is normal 1 2 3 4 is used, that is wrong actually. Okay, so Roman numeral always used. That is rule number 5. Number 6, there is a specific kind of ligand, that is bridging ligand, may be present. Suppose there are two metal moiety and it is joined by some bridging ligand. Suppose M and M, or it may be different metal. It is joined by some ligand. So this ligand will be called bridging ligand, and you have to use the prefix. Prefix means the term that we use before the name. Suffix is which we use after the name. So it will always be suffixed by prefixed by mu. So its pronunciation is mu, mu, but we use this type of term. Okay. So see example of bridging ligand. In this coordination sphere, one left hand side we have CO attached with 5 ammonia, right? And another side we have another cobalt, but that is attached with 4 ammonia, 1 water. And these two are bridged by NH2. So NH2 is common for both parts, and all these are present inside the coordination sphere. Outside you have 5 chloride. That means here charge is +5, right? And how we are writing the name? See, first write the left hand side. This is left hand side, this is right hand side. So left hand side you have total 5 ammonia. Don't consider the bridging ligand, that will come later. So we are using pentaamine, cobalt 3. Now if you are thinking how we are getting oxidation state, I am coming to that point later. Right now just see pentaamine cobalt hyphen mu, which is used for bridging ligand. Then another hyphen. Now the name of the bridging ligand is amido, because NH2 minus, under normal condition what we say, how we call it, amide. So it will be, it is ending with ide, that means it will be now converted to O. So amido. Then right hand side part, tetraamine, 4 amine and 1 water, aquo, cobalt 3. So this full part, it is the name of the core complex cation. So this is complex cation because positive charge is there. And now 5 chlorine outside in the form of Cl minus, so that is by chlorine. Now don't think that you have to mention how many chlorides are there. That is not required to mention, and because it is already understood 5 chloride will be there. Why? Because suppose you do not know the picture and this type of structure is this type of name is given and it is asked that draw the structure, then that is how it look, formula you have to write, then you can easily understand that there are 5 chlorine. Why it is so? Because total positive charge for each cobalt plus 3, so it will be plus 3 into 2, that means plus 6. Okay, and there is all neutral ligand, ammonia, water, all are neutral, but the bridging ligand that is carrying single negative charge, that means -1. So plus 6 minus 1, what you are getting? You are getting plus 5, the charge for the coordination sphere entity. So to balance this plus 5, obviously you require plus to balance this plus 5 charge, obviously you require 5 chloride. So individually you don't have to mention that, and that is also not done. If you do so, that will be wrong. Okay, and here how if the question arises, how we are understanding that plus 3 charge is there, because when the formula is given, you can see here that total 5 chloride, that means you can easily understand plus 5 charge is there. And when you know that plus 5 charge is there and inside there is only one anionic ligand, which is this bridging ligand, that means total positive charge for 2 cobalt, it is plus 6, because plus 6 and -1 together it is making plus 1. So for both cobalt, if it is plus 6, so for individual cobalt it will be 6 by 2, that is plus 3. So in this way we can understand that it is plus 3 charge carried by both the cobalt. Any doubt? Another example we will see. So in the left hand side part, now see outside there is no anion mentioned. It is simply carrying 4 plus charge. So this is a cation. It is not neutral species. Left hand side, cobalt is associated with 4 ammonia. So tetraamine cobalt. Now we are having 2 bridging ligand, O2, NH2. But it is not simple O2, it is actually O2 minus. Now O2 carrying single negative charge, that is known as superoxo. Okay, you know, peroxo linkage is this one. 2 oxygen attached by single bond, 2 negative charge. This is peroxide. Oxide is simple O2 minus. And superoxide is 2 oxygen atom carrying single negative charge. So here we have 2 different types of bridging ligand. One is superoxo, another one is simple amido, that you have already seen in the previous example, how amido is the bridging ligand. So left hand side part, first you will write tetraamine cobalt 3 and then mu amido, mu superoxo. 2 different bridging ligands. So mu is coming twice and A comes alphabetically before superoxo, so that is why we have written it first, then superoxo. And after that, the left hand side part, the right hand side part, which is again tetraamine cobalt 3. Now here how we are getting this plus 3 charge, because it is plus 4. All the ammonia, they are neutral, but superoxo is carrying negative charge, NH2 is also carrying negative charge. So if there are 2 negative charge inside, but still outside 4 positive charge is present, that means both cobalt together is carrying plus 6 charge. So for individual cobalt, it will be plus 3. Any doubt? Should I repeat? These are comparatively complex when there is bridging ligand. And the last one, it is symmetric. See, both side and the bridging part, everything is so symmetric. So now what we'll do, first we have written di-mu-chloro because the bridging ligand is coming twice. And this moiety is same both sides. So that is why now it is written bis and then inside diamine platinum, because this part is diamine platinum, this is another diamine platinum. And how we are getting this charge? Because 2 chloride, that means positive charge is 2 plus, and each chlorine is carrying -1. That means the platinum, it must carry +2 charge each. So total positive charge will be +4. Total negative charge -2. 2 plus is extra, that is mentioned outside the coordination string. So now we have written diamine platinum 2 inside the bracket, because this term is coming, sorry, this bracket will not be there. Here first bracket is already used there, so that is why third bracket is used after this, and then it is ending with chloride. And as I have already said, how many chloride, that you don't have to mention, it is already understood. So in these 3 examples, which are comparatively complex, so if you have any doubt, please mention. Any doubt? Now remember, in some cases what happens, common names are traditionally used, though there are iupac names that should be used, but the historic names, because of historical reason, because the common names are so popular that they are called by their common names. Okay, so for example, FeCN6 3 minus, if you consider this anion, then FeCN6 4 minus. Okay, 3 minus 4 minus. They are named as ferricyanide and ferrocyanide respectively. Ferri is for the first one because their positive oxidation state is +3, their oxidation state is +2. So ferri and ferrocyanide, these terms are used. Remember, these are not exact iupac name, because if it is iupac name, how it should be? It should be hexacyano, then we will write ferrate. Okay, but we are not using that term. These terms are more important because of this traditional use. Okay, and also this FeCO5, how it should be called according to iupac, pentacarbonyl iron, right? But it is simply called iron carbon. So if it is said that iron carbonyl, you have to understand this FeCO5. So these are some examples where for historical reason common names are still used. Okay, here we have some formulas given, and what you have to do, you have to write the systematic names for all these coordination compounds. And if you observe carefully, you will see all the different types, that is all the possibilities, everything is mentioned here. Because sometimes the cationic coordination sphere, it can carry positive charge. Sometimes with this positive part there may be some counter ion, suppose X minus. Sometimes the coordination sphere, it may carry some negative charge, single negative or double negative, whatever it is, and then it is balanced by some metal, suppose sodium. So these are the different possibilities, right? And another maybe example where you have a moiety within coordination sphere but there is no charge, neutral. That is another possibility. And the fourth possibility is two coordination sphere. One is cationic, another one is anionic. So all the different possibilities here you can find. So the first one, outside the coordination sphere, we have single positive charge. That means it is cationic complex or cationic coordination complex. Then the second one, it is carrying -1 charge. So it is anionic coordination complex. Now the third example, here 3 chloride, that means 3 plus charge. So here you have the coordination part is cationic, but you also have counter ion. So overall the molecule is neutral. The first two examples, they are actually still carrying some positive charge or negative charge. But the third one, coordination part is cationic, that is fine. But ultimately the charge is balanced by 3 chloride. So this is overall neutral. Number 4 possibility, now the cationic part is anion, but it is neutral because of presence of 4K plus. Here total negative charge is 4 minus. Fifth possibility, C, this is completely neutral, PTNH32Cl4. So outside the coordination sphere, you do not have any charge and no question of counter. Then the sixth possibility. Now you are seeing something which you have not seen before. This is completely new type of example. In both coordination sphere, you have silver, but ligands are not seen. And one will be cationic, another will be anionic. Okay, so overall it is neutral, but you have complex cation, you also have complex anion. The seventh example. Now this is also carrying, this is actually complex cation, that is same as the first example, but here we have taken a special kind of ligand and NO2, and see how it is written. It is not written as NO2, it is written as ONO. And why it is written in this way? Because it means NO2, as it is bidentate ligand, it can interact through nitrogen or through oxygen. So when it is written in this way, it means it is now interacting through oxygen with cobalt. That means cobalt ONO. Okay. But if it is written simply NO2, then it means the another thing. So now we will see the names. So CrCl2H2O4, here the metal is part of the complex cation. So the name will be ending with simple chromium. You have 2 anionic ligand, 4 neutral ligand. That means if the oxidation state is X, then X minus 2, which is coming from 2 chloride, and overall charge outside is +1. That means here oxidation state of chromium will be +3. So in this way you can calculate the oxidation state. Similarly, for the second complex, chromium, there is -1 charge. That means 4 negative charge is coming from 4 hydroxy. So chromium must be having +3 charge, because then only 1 negative charge will be extra outside, right? So the name is, for the first one, tetra-aquo, and then it is dichloro, because A is coming first alphabetically compared to C. So tetra-aquo, dichloro, then chromium. See, it is not chromate, it is simply chromium because it's part of the complex cation. Oxidation state, and you have to end the name with ion because it is carrying some charge, it is not neutral. And the second one, tetrahydroxo, because under normal condition it is hydroxide ending with IDE. So it will be now converted to O, hydroxo. But as chromium is now part of anionic complex, so the now name is ending with 8. Try to understand the difference with the previous one. It is simply chromium, it is chromate. Then 3, an ion will be there because it is negatively charged. Fine. Then the fourth and third one, first amine is mentioned, then aquo, because this is A, this is A. Then how you will decide? Just go to the next alphabet, M, Q. M comes before Q. So that is why triamine, then triaquo, then chromium 3 is oxidation state, and ending with chloride, because chloride is the anion, anionic part always ending with IDE, not chloro, chloride. Then potassium, see, cationic part is named first, so we have written potassium first. Then hexacyano, not cyanate, cyano, and ferrate, because now iron is part of anionic complex. Oxidation state 2, because outside charge is 4 minus, 2 plus charge, 6 negative charge from Cn, so 4 minus. Then the next one is for platinum complex, diamine tetrachloro, and A is comes before C, and then platinum 4, because oxidation state is because of this 4 chloride oxidation state. Then the sixth one, it is interesting. See, this is the cationic part. So diamine silver 1, it is simply silver, but the second silver, how it is written? It is written as argentate. Remember, it is part of anionic complex. So here it is +1, but 2 negative charge coming from cyano, so overall charge is -1. And in the first case, it is +1, and outside the coordination sphere, this is also +1. Last example, 3 types of ligand, chloro, nitrito, amine. Amine will come first, A, then C, then N. But after nitrito, we have mentioned O because it is interacting through O. Cobalt is part of cationic complex, so it is not cobaltate, it is simply cobalt 3. but as there is positive charge ion, you have to write. So in the next day we will see some names will be there and you have to write the formula. That is the other way that is possible. So regarding all the class, regarding all the slides, is there any doubt? So we are ending the session here. Thank you for listening.